This video we're going to be discussing some more transformations. Actually going to be finishing up this little module on transformations, but specifically non-rigid transformations. So you may have heard me say rigid transformations in the last few videos that we made, and all that really is confronting is the fact that you know, if I had necessarily a function, you know, like a parent function, maybe like a parabola like this. A rigid transformation would be any transformation that maybe shift it left or right, you know, so move it rigidly about the plane, or maybe even reflected. Maybe if we reflected it, it would open down, or reflected about the y or about the origin. Regardless, rigid transformations are rigid because they are very, you know, for lack of a better word, rigid. So, anyways, we're going to be discussing non-rigid transformations. So I guess I'll go ahead and point this out, and we'll observe this in a minute. But and we're going to consider this parent function here, the absolute value function, f of x equals absolute value of x. But you're going to find that it actually does not preserve the shape of the graph. It's really what we're looking at in terms of rigid. I know that I kind of remember it as movement about the plane, and that's how I remember rigid, and that's how I explained it. But mathematically, in a mathematical sense, we discuss rigid transformations as being those that preserve the shape of the graph. So in this case, we're going to take a parent function, this absolute value function, and graph it. But we're going to change the shape of it and just kind of observe what changes in a function would necessarily present changes in a graph. Okay, so let's start with this. We'll go ahead and graph f of x. I'll designate it in blue here, but this blue color. And so we say f of x, of course, just to be very clear on this, you know, I want to, you know, show you why this works here. We say -2, -1, 0, 1, 2. We call that our subset of the domain, and we'll go ahead and plug these into the function. But for example, you know, we say f of -2. The function value at -2 would be the absolute value of -2, which would be 2. So let's go ahead and proceed back here. 1, 2. I'm going to go ahead and fill out a little bit here on the x-axis. We're going to be graphing some other graphs, so I think this would be, you know, appropriate. So anyway, so -2, 2. So we're up here at 2. If we plug in -1, absolute value of -1 is +1, so we get a height of 1. We come down to 0, 0. Suppose I could be filling these in a 0, but when we plug in 1 and 2, of course, we bounce back up positive. So we have our typical parent function here, the absolute value function. Looks like this. Bounces up and always makes a v. Okay, we're going to label this. I'm going to call this f. Okay. So now let's kind of explore some non-rigid transformations, starting with how about a couple of other functions here. So I'm going to change both of my colors here. We'll go like a green and a red. But we're going to call this next function, since that's f, we'll call this one g of x. And g of x will define as being 3 times the absolute value of x. So something different than what we started with. And then we'll call in pink here, we'll call this one h of x. Excuse me, we'll call h of x 1/3. 1/3, okay, the absolute value of x. Why not work with the reciprocal here, but a nice proper fraction. Okay, so just kind of showing how this would necessarily affect the mapping going on. And that's why I made the table up here, even though we all know what this graph looks like, but excuse me. Let's plug in the same x values. We're rocking here, -2, -1, 0, 1, 2. But check this out. When we plug it in this time, we say, so f of -2 is going to be 3 times the absolute value of -2 when we plug that in. So in other words, that's 3 times 2, we get 6. So all of a sudden, already you're seeing at -2, we've already extended the height of this graph. And you know, one could already start to surmise that you know, this point over here will be on the graph. Of course, we could test for y-axis symmetry by plugging in a -x and finding that we get the same thing with our function. But just kind of already thinking about what's going to go on, because the next point I'm going to plug in here, we say 6 here. I'm going to plug in 0 because it's easy to work with. But of course, the absolute value of 0 is 0, and 3 times 0 will be 0 as well. The interesting thing about this graph is, you know, already kind of talking about how it's going to come down here, and we'll plug in those other 2 points here, but you can see already that it's been stretched, is what I'm going to call it. I'm going to call it stretch, and specifically vertical stretch, because it's kind of stretched upward is kind of the way I want to think about it here. It got skinnier, it stretched upward, it's slimmer, okay? But this is vertical stretch, okay? So what if we plugged in, say, 1? 3 times the absolute value of 1 would be 3, and then here we'd also get a +3. We can check that, of course, but those are those other 2 points right there. So already seeing this going on here, we say, you know, 3 times the absolute value of x, or one could necessarily kind of restate this as, since the absolute value of x was the same as f of x in the first place, we could have rewritten this as g of x is equal to 3 times f of x. And we'll come back and visit that rule right there. Okay, over here to the pink, make a mapping here. We say x, y, we'll go with the same x values. This will be interesting. You'll see. 1, 2. Check this out. We plug in -2 this time. -2. Okay. The absolute value of -2 is of course +2, and 2 times 1/3 is going to be 2/3. What I want you to see is that already we're dealing with something. You know, last time it went up to 6 at an x value of -2. Since we get a 1/3 out here, a proper fraction out here at the moment, it's basically going to take all of the x values we plug in and diminish them. So in other words, at the same x value as what we started with in blue, it's actually going to be shorter. So we say at -2, we're here now at a height of a positive 2/3. If we plugged in 1, of course, the absolute value of -1 is 1, and 1 times 1/3 is 1/3. But now we're at an even shorter height than last time. Technically a third of the height we were at last time. And then plugging in 0, we're going to get this 0 here. So for the sake of time, I'm going to go ahead and plug in these other 2 points here. This is symmetrical. But we still have a v. But you're going to notice in this case, I'm going to call it, you know, say like wider. Okay? Or you can look at the slope of each individual line. Its magnitude is dropped. But regardless of how you look at it, you can notice that our graph here, I'm going to call this also vertical stretch. But what it's done is it's necessarily gotten wider. Okay, so this kind of this pattern here holds for all of our functions when we start to rock some of these transformations. Real quick before we move on, check this out. Again, the absolute value of x was just f of x up here in the parent function in the first place. So instead of writing 1/3 the absolute value of x, we could actually get away with saying 1/3 times f of x. Okay, so 1/3 times f of x. But you'll notice in each case here, we were able to rewrite the new function g of x and h of x in terms of f of x, okay? And in each case, we were taking f of x times a number in front of it. So what I want to do is kind of generalize this now and say, okay, so, you know, in general, okay, in general. We'll split up these videos here. We'll do another one on horizontal stretch, but kind of similar. But in general, if we say some function h of x, we'll call it h of x, is equal to, we'll call it c for some constant times f of x, okay? Then we have vertical, and I'm going to put in quotation marks here, stretch, okay? Because, you know, we did have one that got wider, but it's still stretching in a vertical sense. Stretch, okay? So 2 clauses here of this conditional statement. We say, okay, so if we say just the magnitude of c, okay? So if absolute value of c is greater than 1, then, you know, we say vertical stretch, okay? Well, let's just say this. It gets skinnier, okay? And if c, this is interesting here, it's a compound inequality. We say c, the absolute value of c is greater than 0, which just means, and less than 1, just means it's a proper fraction. You want to look at it like that. When we say vertical stretch, but we get wider, okay, or flatter, slash, okay. And then one last thing here, we say if c is negative, just the value of c is less than 0, negative, and we could say things open downward. Now this is kind of an addition here that I'm putting in. If you think back to our other videos, of course, if c is negative, okay, this number in front of f of x here is negative. That's kind of like saying negative f of x, okay? And negative f of x, we know from our other transformations, just makes it open down, okay? Or it reflects it. It would reflect it. If you make, you know, y negative, it would reflect it about the x-axis. So making y negative, cast it about the x-axis. Okay, so in the next video, we'll talk about horizontal stretch.